How do we solve an equation that looks like this? It's a rational equation because it has a polynomial in the numerator and the denominator. For all types of equations like this, to solve them, it's very similar to solving polynomials actually. It's just going to take a little bit of algebra, but we need to be a little bit more careful with our restrictions, especially what happens in the denominator. So for example, how are we going to solve this equation? Well, right off the bat, what are our restrictions going to be? We know that the denominator can never equal 0, so we know that x cannot equal 1, right? That's right off the bat. So then how do we solve it? Well, we can solve it by clearing the fraction. So there's a denominator of x minus 1. We can clear the fraction by multiplying by the lowest common denominator, or in this case, just cross-multiplying, right? If we cross-multiply this x minus 1 up to the top, another way of thinking about it is just multiplying both sides by x minus 1, but all we're left with is that x plus 3 equals 0. And then we can just quickly solve that for x, right? Negative 3. So that's our solution that we get there. Because rational functions can be a little bit more complicated, it's always a good way to check to make sure our answers that we get work. So that's why I've included a little check thing on the side. All we have to do to check is plug negative 3 into our equation and see if it works out. So this gives us 0 over negative 4, which gives us 0, right? Which checks out with what's on the right side of that equation. So there we go. We're set. So this is our final answer. X equals negative 3. Okay, that first one maybe you thought was a little bit too easy. So let's go to one that's a little bit more complicated. We now have a rational function on one side and a polynomial function on the other side of the equal sign. So again, we should start off by looking at what our restrictions are, right? The denominator can never equal 0, so that x minus 1 in the denominator cannot equal 0. This tells us right off the bat x cannot equal 1, right? Now, let's clear that fraction. So we can clear the fraction, but again, we can look at it as cross-multiplying, but really what we're doing when we do that is multiplying both sides of the equation by x minus 1, or both sides of the equation by the lowest common denominator. So essentially what I'm going to do is I'm going to multiply this by x minus 1, and then if you want to show it, x minus 1 on this side as well, those just are going to cancel out, and then that's going to multiply. So what we end up getting is x plus 3 equals, and I could just distribute that out, 2x squared minus 2x plus x minus 1. And then, of course, simplifying and setting it to 0. Same as a polynomial function, right? So 2x squared minus x minus 1 minus x minus 3. If I move everything over, that's going to equal 0. And then, once again, simplifying. So 2x squared minus 2x minus 4 equals 0. How do I solve this? Well, whenever we have a polynomial that's higher than basically a linear polynomial, we can always solve by factoring, or we can always try to solve by factoring. So first of all, I'm going to remove a greatest common factor, 2x squared minus x minus 2 equals 0. And then we're essentially able to divide both sides by 2, which gets rid of that 2 there, right? So then we're left with 0 equals x squared minus x minus 2. And can we factor this? Two numbers that multiply to give us negative 2 and add to give us negative 1. Yep, the answer should be x minus 2, x plus 1. And that equals 0. So from this, what are our solutions? Don't forget, don't get to this factoring part and then forget to actually find the solutions. The solution from here is that x can equal 2. The solution from here is that x can equal negative 1. So, are those our answers? We can check, right? And it's always a good idea to look back at what our restriction was from the beginning, right? Our restriction was that x cannot equal 1. That doesn't mean anything bad for our answers that we got. So we can easily check by plugging in x equals 2 and x equals negative 1 into our original function, right? So I'm going to start off with x equals 2. And then we'll do the left side and the right side. We'll evaluate those separately because technically that's what we should do. left side is going to equal 2 plus 3 over 2 minus 1, which is going to give us 5 over 1, so just 5, right? And the right side is going to give us 2 times 2 plus 1, which is going to give us 5. So x equals 2 checks out. We can try the same thing with x equals negative 1, left side and right side. So on the left side, it's going to be negative 1 plus 3 over negative 1 minus 1. The right side is going to be 2 times negative 1 plus 1. And if we evaluate both of those, we're going to get 2 over negative 2, so negative 1 over here. And we're going to get negative 1 plus, or negative 2 plus 1 is negative 1. So that also checks out. So we're good. Our final solution is x equals 2 and x equals negative 1. Ooh, now we're getting a little bit more complicated here. This is where all that grade 11 algebra is going to kick in. So we need to solve this equation, and we have two separate rational functions basically that are being added. There's more than one way to approach this problem, but I think one of the easiest ways is just to be able to combine these both into one rational function, right? We can't do it as it is because we can't really multiply this x plus 3 at the top because we still have this x plus 2 over here. It's going to get complicated. So instead, let's combine these two into one rational function. In order to do that, we need to find the lowest common denominator between those two. They're already factored, so we don't need to factor anything, but factoring is always a good first step. Oh, and actually, before I go too much further, let's include our restrictions. So our restrictions in this function are that x cannot equal negative 2 and negative 3, right? That's always a good first step to take. Anyways, getting back to the rational functions. What we can do is we can find a lowest common denominator in order to multiply both of these rational functions by, right? And that will basically simplify it into one equation. So we have in our first rational function x plus 2 in the denominator, and in our second one we have x plus 3. There's nothing in common, so we could basically multiply that first one by x plus 3. This gives us a denominator of x plus 2, x plus 3. In the second one, we also can add, well, it's 24 over x plus 3, but we can multiply by x plus 2 to give us that common denominator, x plus 2 over x plus 2. And this all equals 13. Don't forget about that 13. So notice now how we have common denominators. We have an x plus 2, x plus 3, x plus 2, x plus 3. So now we can just add those numerators. So just simplifying a bit, 1 times x plus 3 is just going to be x plus 3. And then we're going to add to that 24 times x plus 2. And the denominator is just going to be x plus 2, x plus 3. And that all equals 13. Now, can we cross multiply now? We can, right? Because we have them all as one fraction, and we can multiply both of these terms up to the top here. Or you can think of it as just multiplying both sides of the equation as x by x plus 2, x plus 3. So let's just multiply that up. So we're going to end up on the left side. I'm actually going to simplify as we go to x plus 3 plus 24x plus 48 equals 13x plus 2, x plus 3. So you can expand and simplify this. What we're going to do is we're going to expand and simplify, set the equation to 0, and solve. Same as any polynomial, because now basically all we have is a polynomial equation. So I want you to pause the video here, do all that algebra, and then check in, unpause when you're done that. So this is what you end up with. It's a quadratic equation. It's not that pretty. So we can try to factor it, or we could use the quadratic formula. Normally I would say this is way too complicated to be able to factor, but just a very quick glance. There's a little bit of a trick to notice here with equations that look like this. Remember, we're looking for two things that multiply to whatever 13 times 27 is and add to get 40. But if you catch it, there's a little trick here where 13 times 27, doesn't really matter what that is, but what's 13 plus 27? It gives us 40. So aren't the two numbers that are going to multiply to 13 times 27 and add to 40 just going to be 13 and 27? And the answer is yes, it will. So if you can spot this trick, it's actually going to help you out factor stuff sometimes. It's not always going to work, and you could always use the quadratic formula for this. So it's going to be 13x plus 27x plus 27. And then we can factor this 13x, x plus 1 plus 27x plus 1. There we go, and factoring that one more time, 13x plus 27, x plus 1. There we go. So zooming back out here again, what are our solutions from this? Well, from that left one, 13x plus 27, that tells us that our solution x must be, what is it going to be, negative 27 over 13. That should be a 27, not a 20, whatever that it was. 27 over 13. And our other side says it's going to be negative 1. There we go. So there are our two solutions. And you can use the quadratic formula. You should get the exact same answer. Now, we should go ahead and plug those back into our original equation to see if they work. I'll let you do that part. I actually just happen to know that that is the correct answer. So feel free to check your solutions. It's something you should always do. But these solutions will both work. One thing to check also, do they conflict with our restrictions? And the answer is no, those aren't restrictions, so we should be good. Okay, so here we get to example 4. There's actually lots of ways to go about this problem. I'm just going to show you one, but note that there are many. First of all, the first thing we should do is take into account our restrictions. So we know right off the bat, x cannot equal what? Well, anything in the denominator, anything that makes the denominator 0. So 2, 1, and negative 1. Cannot be any of those things, right? Now, the approach I'm going to take to solving this problem is similar to how we did the last question. I'm going to combine these two terms by finding a lowest common denominator, which is just going to be x minus 2, x minus 1, and then cross multiply, simplify, and solve. Basically set it to 0 and solve. You could also bring this to the other side and then find a common denominator for all three terms, but that's just going to get even more messy. It ends up being the same thing in the end, so it's just up to personal preference how you want to do your algebra at this point. So as I said, I'm going to find a common denominator of x minus 2, x minus 1. I'm going to skip a few steps on this time because hopefully you understand or you can follow along with what I'm doing. So 7 on the left needs to be multiplied by x minus 1, right? And then the minus 4 needs to be multiplied by the x minus 2 to make that work out. And this all equals negative 3 over x plus 1. Now what I can do, because now I have one term on the left-hand side, or one thing in the denominator, now I can do my cross multiplication, right? So essentially I got to multiply everything on the top, so this term and this term, both by x plus 1. It's going to be a lot of algebra, but we got to do it. So 7 x minus 1, and then it says, as I said, I'm going to multiply everything by x plus 1. Minus 4 x minus 2 x plus 1, because this over here has got to be multiplied by each thing. And then on the other side, I'm going to have negative 3 multiplied by the denominator, x minus 2 x minus 1. Okay, now it's just a lot of expanding, simplifying, and solving. So again, pause the video here, do all that, and unpause when you have your final polynomial at the end. So here's our final polynomial. Now, can we factor this? You can try, but if we do a quick check with the discriminant, so if we do b squared minus 4ac, that's going to give us 25 minus 4 times 6 times 7, and that's obviously going to be less than 0. So therefore, this polynomial, or this quadratic here, has no solution. Now, does that mean the equation has no solution? Looks like it, right? Because any solution for this equation up here should be in common with any of these solutions here. So it looks like there's no solution. Before I wrap up the video, I just want to show you what this looks like graphically. What do you think it means if there's no solution to this equation? Think about it for a second, and I will show you the graph. So looking here, I've graphed the two sides of that equation, for example, 4, as separate equations in Desmos. And we see the top one I have shown in red. The left side I have shown in red. So that's 7 over x minus 2 minus 4 over x minus 1. What should we see when I activate that second equation there? Well, what did we say the solution was to the problem? We said that there was no solutions. So those two equations shouldn't touch anywhere, right? Because any points that they touch means that's a solution. And if I activate it, see the blue? Do those red lines and blue lines ever touch? Well, not here. If I zoom out, do they ever touch? No, even going way to the left. See how the blue one's always above and the red one's always below the x-axis? And the same thing's going to happen, but opposite, if we go to the right. The blue line's always below and the red line's always above. So it looks like both of these functions are asymptotic to 0, but one comes from above and one comes from below. So they're actually never going to touch. So it makes sense. Our answer makes sense based on the graph that there should be no solution to this problem. Desmos is a very easy way to quickly check your answers. And remember, just plug in the left side and the right side of the equation as two separate functions in Desmos.